So in this class I'm going to introduce something called the principle of conservation of linear momentum. And the principle of conservation of linear momentum says for a collision occurring between objects 1 and 2 in an isolated system, the total momentum of two objects immediately before the collision is equal to the total momentum of the two objects immediately after the collision. And that's important that we're talking about immediately. We're not talking about an hour before or an hour later. We're not even talking about a second before and a second after. We're not even talking about a nanosecond before and a nanosecond after. We're talking about an instant. And between two consecutive instants, really there is no change in time. So that can be a tricky thing to wrap your head around. But what we're talking about is you've got two objects here, maybe they're both moving, maybe only one is moving, maybe they're moving in opposite directions, maybe they're moving in the same direction with one catching up. But if there's a collision, just immediately before the collision, the total momentum in the system, which will be the total momentum of object 1 added to the total momentum of object 2, that will equal to the total momentum after the collision. And the principle of conservation of linear momentum, which is written out on page 51 of your formula and tables booklets. And just make a note of that up there. Formula and table booklet, page 51. Make sure you can find it. It's the principle of conservation of linear momentum. It says m1u1 plus m2u2 is equal to m1v1 plus m2v2. U being initial velocity, v being final velocity. m1u1, that's the momentum of object 1 initially. There's the initial momentum of object 2 will equal to the final momentum of object 1 plus the final momentum of object 2. Total momentum before equals total momentum afterwards. So I want to look at this example here. I've just written out in a table format to save me writing out a whole load of English. So I've got the mass of object 1 is 2 kilos, the initial velocity of object 1 is 10 meters per second. The final velocity of object 1 is 1. The mass of object 2 is 3. Initially object 2 is moving with a velocity of 1. Note in this case object 1 and object 2 are moving in the same direction. They both have a positive velocity. That means they're both moving in the positive sense. So maybe they're both moving to the right, but one of them is catching up with the other. And there's a collision takes place. What do you think would happen? And again, you could probably guess, a couple of things. I can only move one object at a time on my board, but if this is moving to the right and this catches up on it, you would imagine this object on the right would speed up and the object on the left would slow down, or maybe even turn, who knows. But the object on the right would keep moving to the right, which we would guess that would mean this is going to be, I would guess that would mean that this is going to be a positive velocity and probably greater than 1. Okay, so let's look at applying the principle. Two objects come into contact. There's a collision. And the principle of conservation of linear momentum. And I recommend always writing that out, PCLM, every time you're going to use it. m1u1 plus m2u2 equals m1v1 plus m2v2. Total momentum before equals total momentum after. m1u1, well, m1 is 2, u1 is 10, so that's 2 times 10. Plus m2v2, well, m2 is 3, and, m2u2, I should say, m2 is 3. u2 is 1, that's going to be 3 times 1. And that's equal to m1v1, well, that's 2 times final velocity of object 1 is 1. Plus m2v2, m2 is 3, times whatever v2 is. That's what we're trying to find. So fairly straightforward from here. It's just a linear equation. On the left we're going to get 23, and on the right we're going to get 2 plus 3 times v2. Excuse me. Subtracting 2 from both sides, we get 21 is equal to 3 times the velocity of object 2, and then dividing by 3 on both sides, we get the velocity of object 2 is 7 meters per second. Notice it's positive. 7 meters per second. Positive. So, what has happened? What has happened? Well, the first mass has, its velocity has gone from 10 down to 1 in the collision. Notice the collision there is the initial velocity of object 1, final velocity of object 1. And this makes sense. If it catches up and clashes into something, it should slow down. So it's slowed down from moving 10 meters per second to the right to moving 1 meters per second. Still to the right though, it's still positive. The second mass is moving initially to the right at 1 meter per second, and then there's a change. There's a change in velocity. And it gains, velocity. It was moving at 1 meters per second, but what happened when this caught up with it and slammed into it is it caused it to speed up. So those things should make sense. Those things should make sense. Let's think about this. I want to look at the change in kinetic energy of object 1. So I'm going to look at the change in kinetic energy of object 1. So to find the change in kinetic energy of object 1, what do I do? Well, the change in kinetic energy will be equal to the final kinetic energy minus the initial kinetic energy. Ek final minus Ek initial. Kinetic energy is divided as a half mv squared. So half times mass times the square of the speed. And notice we use speed here, minus a half times the mass. And initial kinetic energy will be using the initial speed. The thing I'm noticing there as well is I can factor out a half m. The m isn't changing in an object, so that's m over 2 times v squared minus u squared. And that's a nice little formula for finding the change in kinetic energy of any object. So I'm looking at object 1 here. Its mass is 2. So mass over 2, let's write it in, 2 over 2, times v squared minus u squared, final velocity squared minus initial velocity squared, 1 squared minus 10 squared. So that's 1 times 1 minus 100, that's negative 99, which is of course just negative 99. My units there are joules. So my change in kinetic energy is negative 99 joules. That negative, and that's not a direction, that is just telling me there has been a loss in kinetic energy. So there's a loss in kinetic energy for object 1, has lost 99 joules of energy in this collision. Why? Because its speed got dramatically reduced. So it has lost 99 joules of kinetic energy. Let's look at object 2. Actually, I'll just do it over here. Let me get rid of this out of the way. I'll do this over on the left. I'll look at object 2 here. And I'm looking at the change in kinetic energy, which we said is mass over 2 times v squared minus u squared. So I'm dealing with object 2. Its mass is 3, so I'm going to get 3 over 2. Times its final velocity squared, well that's 7 squared, minus its initial velocity squared, 1 squared. So I'm getting 3 over 2, times that's 49 minus 1 is 48. So half 48, 24, triple it, I think I'm going to get 72 joules. 72 joules. Notice that's positive. Let me just write in that positive sign. That means object 2 has gained 72 joules of energy through this collision. Has gained 72 joules of kinetic energy during this collision. So the total change in kinetic energy is just going to be the sum of these two things. So adding negative 99 and 72. So it's going to be a negative, I think that's going to be 27 joules of energy. So in total, during this collision, this system has lost 27 joules of energy. Where did it go? Well, maybe it went into making sound when they collided, or heat. Some kind of heat may have been generated. Okay, so that's how we use the principle of conservation of linear momentum. Well worth noticing, remember this is not in your tables. Remember the change in kinetic energy for any particle will be m over 2 times its final velocity squared minus initial velocity squared. You're not given that, but you are given this principle of conservation. Do write out PCLM beside it every time you're going to use it. Do write out the full formula. Practice some problems. Okay, so that's the principle of conservation of linear momentum.